So hello everyone. In this lecture, we will see one numerical of combined. They have combined the topic from the isentropic flow through the nozzle and expansion wave, and this kind of combination they have asked this time. So we will try to solve this, and we will see some new things they have introduced in this. So okay, so this question from asked from your gas dynamics, right? And they have combined the flow through the CD nozzle and shock wave. They have expansion wave. They have combined in that. Okay, so okay, and this question was your NAT question and asked for 2 marks. Okay, so okay, let's see the question. So if you see, this was the question number 55, and this was NAT, and I have put the answer as well, so you can cross check. Okay, so let's read the question. A conversion diversion nozzle with adiabatic wall is designed for an exit Mach number of 2.3, right? So at the exit we have a 2.3. They want 2.3 at the exit plane of the nozzle. It is discharging air to atmosphere way under the condition indicated in the figure, right? Okay, so they have given this kind of expansion fab and some designing point we want, designing property we want at the exit, which is PA and TA they have given, right? So now flow through the nozzle is envisaged and the characteristic gas constant blah blah blah, they have given everything. When the reservoir pressure is 25 bar absolute, the temperature is 300 Kelvin, Prandtl-Meyer expansion wave appears at the nozzle exit as shown. Okay, so this is expansion fan. I hope you know that. Anyone who have prepared gas dynamic, they know what is this and what will happen across the expansion wave, the all the properties, so static and stagnation. The minimum percentage change in the reservoir pressure required to eliminate the wave system at the nozzle exit under steady state is okay. Now they have asked the what percentage I will change in the stagnation pressure of the reservoir so that I will directly eliminate, I will not get the expansion wave at the exit of the nozzle, right? So this is the question they have asked, and regarding that they have given the all properties of the stagnation and static. Okay, so let's understand first. So they have given the exit Mach number, right? Nozzle exit Mach number, which is 2.3, and this is supersonic, right? So for we know that for the getting supersonic at the exit from the nozzle we need a convergent divergent section, right? So already they have, this is kind of checkpoint. Okay, so with adiabatic wall, right, they have given adiabatic wall. That means what they are saying, your heat will not transfer from the wall. Okay, I will tell you what another mean it is. It is designed okay, they have given everything. It is discharging air to the atmosphere under the condition. That means air is going out at the atmosphere, and the atmosphere properties they have given also. Okay, let me write first the given data, then we will discuss. Okay, so if you see the reservoir condition they have given, okay, I'm writing it as this. I hope you understand what is P naught and what is P. I'm not going to that. Okay, okay. Because the reservoir, in the reservoir the velocity is almost zero, stagnation and static both properties become zero. If I take the advantage example of temperature, I hope you are aware of this equation. So in a reservoir we know that my velocity almost zero, negligible. So because fluid is stationary at that condition, so your, this is stagnation temperature. Total temperature is represented by static plus dynamic, right? So we don't have a dynamic temperature. That means your whatever static temperature you have, whatever total temperature you have, that is nothing but your static temperature, right? In the case of reservoir, I hope you understand. Okay, okay, fine, we understand that. Okay, now if you see, yeah, everything is given. Okay, let me write all this. 300 Kelvin. And the atmosphere, this is PA, which is atmosphere, right? Atmosphere property. Okay, this is 1 bar, and TA is nothing but 300 Kelvin. Fine. And some gamma is 1.4 they have given, R is 287. Okay, okay, fine. Now if you see, now they have asked what percentage change we will do so that my expansion wave, this expansion wave will eliminate. So why expansion fan is came here. So first we will discuss that. Okay, so expansion fan, across expansion fan, what will happen, that across expansion fan your velocity will accelerate. Your velocity will accelerate. That means when your velocity accelerate, in that pressure will decrease in that case, and corresponding your Mach number will increase in that case. Okay, so expansion fan generated here because your at the nozzle exit your pressure is more than the atmospheric pressure. That means this kind of thing, your exit nozzle pressure is greater than the atmospheric pressure. That's why this expansion fan is generated. So to eliminate that, we need to change the reservoir condition. This is the important thing. Okay, I hope you understand. So what percentage we have to change so that your expansion fan will eliminate, this is asked in question. Okay, so if you see, there we have this thing. So they have given the this uh, this checkpoint they have given flow through the nozzle is envisaged, right? And they have said adiabatic wall. This both the things are indicating what? Can you tell me? This both the things in indicating the you need to consider that flow is isentropic flow across the nozzle. You need to consider it as an isentropic flow. That's what they are indicating in that. What does it mean? Now whatever equation I will use, that will be the isentropic equation. Okay, so if you know this equation, isentropic equation, now this becomes your P naught. Let me writing it as a 1, which is reservoir. It will be also equals to P naught E, right? Because we need not to worry about the friction. Okay, so and boundary layer, many things. So they have said isentropic, so we need not to worry. P naught 1 will be also equals to P naught E, right? Both the stagnation pressure will be conserved. Now if you see this formula, I hope you have remembered what formula this is, right? So if you calculate, if you know, we know this thing P naught E and ME, we know that we can calculate PE from here. Why I'm calculating that? Because I will get PE in this condition, and we can then we can compare that PE with the PA exit pressure, and we can compare with sorry, with the atmospheric pressure. Then we can predict what percentage we need to change with the reservoir so that I will not get the expansion fan, right? Okay, let me do that. Okay, if you do in this, if you put m equals to m equals to 2.3, they have given exit Mach number, and this you will take it as a 25 bar. If you solve this gamma, I hope you know that this is 1.4, that means air is flowing in that. So if you calculate all these things, I have already done this, so you will, okay, let me do this also. This you will get this as a 25.5042, and if you calculate PE from here, this is nothing but 25. If you calculate PE from here, you will end up with 1.9993 bar. Okay, I hope you don't mind if I write it as a 2 bar, right? Because this is, if you can directly, you can say this is 1.993 bar, so I will take it as 2 bar. Okay, no issue, completely fine. So that means now understand this. This is your nozzle, right? And this kind of expansion fan is generated, the exit. Now okay, this is your exit. Okay, this is your exit, and understand this is your atmosphere. Now if you see, you are getting P exit as a 2 bar, okay, and PA you have a 1 bar. Hope you understand. Now what changes I will do, that from 2 bar to 1 bar I will get. So I need to change the reservoir condition in that case. So that means, if I, please tell me, if I change reservoir which is 25 bar, if I change it as a 12.5 bar, if I change half of, if I do half that, so I will get directly 1 bar here, right? At the exit I will get 1 bar, using, provided your ME is still 2.3. okay, let me do that also, then you will understand. Okay, let me erase this. Okay, let me do that, you will understand 100%. So this kind of conceptual question, if only you can solve that if you know the all this minor thing, very expansion fan across that vault will happen, reservoir condition, all this thing. So tell me this now, if you, in the place of, this is nothing but your, this is nothing but your 12.5 now, right? And calculate PE from here using this property, using ME, take it as a 2.3 because they have given already, and gamma is nothing but, okay, 1.4 divided by 0.4. Now solve this equation, solve this for PE, you will get this as a 1 bar, you will get this a 1 bar. So now I have a 1 bar already, provided you have changed the reservoir condition to the half value, to the half, 25 to 12.5. so you have changed the 12 reservoir condition to the 12.5. now you are at the exit, you are getting 1 bar, and we already want at the atmosphere, we want 1 bar. So now my whatever desired thing is, we got it, we want 1 bar and we already got 1 bar. Now there is no point of having the expansion fan, automatically your expansion fan will be eliminated from here, because you have 1 bar here and there is a 1 bar also, so there is no intermediate person in that, there is no expansion fan now. Initially we want expansion fan because my pressure was 2 bar and I want to reduce it to the 1 bar. So nature will always establishes, because you have a higher pressure at the exit, we have a lower pressure, we are going from higher to lower, but nature will stop you there, they want to go hand to hand. That means you have, at the exit you have 1 bar, that means at the atmosphere you have 1 bar, that means at the exit they also want 1 bar, atmosphere want that. Nature will establishes the expansion fan in that condition. So I hope you understand what was the intent they have given, why they have given the question. So they want to check the your understanding of expansion wave also, and the nozzle supersonic nozzles, isentropic flow through the nozzle. Okay, I hope you understand in this, and if you did not get, you can match this. So that means now we want 1 bar, right? Okay, let me complete this also. We got 1 bar also, using, we have changed reservoir from 25 bar to 12.5 bar. What does it mean? We have changed the pressure the 50%, we have reduced our pressure to the 50%, right? I hope you got it, because this is, if you divide 25 by 2, that means half, we have changed the half percentage to the half, 50%, the changes is required to eliminate this expansion wave. I hope you got it, and you can also match this. The answer is given from 49 to 51. That means they have said 40, you have to change the stagnation pressure from 49% to 51%. This is fine completely, they have given very good question this time. Okay, if you did not understand that, You can ask me in the comment section. I will try to answer that. Okay, let's meet in the next lecture. Thank you.